25th of July 2023, and this is the first time I've ever made a video directed specifically at children. And before I start, it'll be interesting to see how YouTube deal with it. They may not like it coming on, I don't know, but I can assure all concerned, and YouTube and Rumble too, that I won't be ever having anything on a children targeted channel that isn't simply basic facts, and not to try to indoctrinate or anything like that. There won't be any of that, or no improper conduct. Now, what I want to deal with here is the basic structure. Essentially, in the universe, essentially we live in a huge, big universe with galaxies as far as any instrument can see, with a limitation on the speed something can travel, based on the speed that is said to be the speed of light, or a limitation in the universe, which is equal to the speed of light. No, that's the big picture. And then we have our own galaxy, the Milky Way galaxy, which you will see on certain nights, and we appear to be looking, we're in the edge of, oh, you're looking at the edge, it's like a disc, so you're sort of looking through it like that. No, that's not exactly right either, but partly that way, and you can see it. And in some cases it's quite dark patches in it, and in some cases quite bright, and that you can get a look at the galaxy. It's convincing enough to convince any ordinary observer, even without binoculars, that we are in a galaxy called the Milky Way. Now, secondly, with really good eyesight on a clear night, and particularly with binoculars or a telescope, you can see the Andromeda galaxy, and you're sort of looking at it sideways, you're sort of looking that way, but you can see enough of it. Lucky enough, it's not exactly on edge, it's a bit that way. You can see that it's a galaxy, and there's no doubt it's a galaxy. Now, we can never see the Andromeda galaxy this way, because we could never get far enough out to look at it that way. But with the aid of the Hubble Space Telescope, and now the James Webb Telescope, and other telescopes, and even telescopes based on Earth, on very high mountains where there's good visibility and no light pollution, they can see galaxies in the distance, and we can see every possible shape. And I highly recommend anyone, with your parents' consent, to watch programs on that, and if you're allowed to watch the internet and that, and put it up on the television, to look at the science programs, and particularly the ones put out by NASA and the James Webb Telescope, and see the wondrous things that are there, and the nebula and all of this. One of these nebula is the Horsehead Nebula, and it's up in the sky in the Orion constellation. And actually, with a good telescope, I personally have seen the red and black blob there, where that is, with a 6-inch reflector telescope. So anyway, that's where we are. Now we move on down, and then we have the sun, and we have our planets, and you know all about them already. You don't need me to explain, but you can see the planets on particular nights, and you can get a very good look at them. And then we have the spacecraft which took better photographs. Grand. Now the moon, of course, is our only moon. We have one moon, and you can see the moons on Jupiter with good telescope or binoculars. And then one of them goes around Jupiter every 5 hours, so it's fairly fast. Now, the next thing then is, when you get to the Earth, where we are, or where I am sitting now, and where you are sitting or standing, you then have matter. The Earth is matter. And what is matter comprised of? I think that's grammatically correct. It's comprised of atoms. Atoms are the basic element of a basic part of an element. So if you take aluminium, if you take iron, if you take copper, helium, hydrogen, they are all elements, and the atom is the basic part. And the atom, there are possibly about 108 or 9, but once they go above about 96, they become unstable, and some of them can only exist for a brief period. But for practical purposes, there are about a little less than 100 atoms, maybe 79, 70, maybe 97, 98. The point is, they become unstable. So when you go up to uranium, think that's 92. I haven't looked it up. You're getting into the area of instability. But for the intervening parts, from 1 to 90, from hydrogen up to 90, you have that number of atoms. And no matter where you look in the universe, that is what you are seeing. You are seeing the elements from 1 up to about 96 or 7. So if we go practical about it, folks, say 95, if that's all right. Now, so that is the case everywhere. And atoms have 3 essential components. They have the nucleus. I might pause this here. Now, you have the proton, which has a positive charge here. See here? You have the neutron, which has no charge. It doesn't have a charge at all. It's independent. And you have the electron, which has a negative charge up here. And these go around each other, all go around each other. For space-wise, if you take it that we'd say, if these were, we'd say the width of, we'd say this marker. They were the width of that marker. Here's a black one, easier seen, apart. Then the electron here would be 2 miles away. You understand that now? So if you take a big football stadium, if the proton and the neutron were only apart, let's say the distance of the lid of that bottle there, then the electron would be 100 meters away. Get the point now. Or if it was a football pitch and the football was the proton, and let's say a handball was the neutron, or a golf ball was the neutron, the electron would be a way out at the far side of the stand, or maybe a way off somewhere else in the location where it is. Okay, now these go around each other. These go around each other, driven by the strong magnetic force, the weak magnetic force. Now, if you get a magnet from the fridge or anywhere else, you can very easily see how magnets work. And if you get 2 together, you'll see that sometimes they attract each other and sometimes they reject each other. So it's the strong and the weak magnetic force, and then you have the strong nuclear force and the weak nuclear force. And between all of those, they allow the atoms to get together in certain conditions and form a molecule. The shape of these atoms is a bit disputed and all that, but here's an example, a hexagonal shape, which is used in nature if you ever go to basalt rocks, such as the Giant Causeway in Antrim in Ireland, in the very north of Ireland, and in many other basalt locations. Nature has to put these things efficiently together. It has to split them up, and the hexagonal, roughly done here, please understand, is one way of doing it, and that's one example. Others say they're sort of round. It's very hard to photograph them. They're tiny, tiny, tiny things. Like, I mean, if you took a grain of rice, you would have more atoms in a grain of rice than you would have people on the planet of the Earth. That's how small and how tiny they are. But the most important thing is that they can form molecules, right? So there's one type where the molecules are all of the one element. So a copper molecule would have nothing in it, only copper. And there are then other ones which could be a mixture, which could be an alloy where the two are formed together. And a mixture is where they're mixed together, but they're not actually chemically bonded. When the electrons and the parts of the atom interlink, they form a chemical bond. So you can call a molecule homonuclear. That's when it's one element only, like copper or oxygen on its own. They're still bonded, but they're bonded to their own element, and they're called homonuclear, like that. Or it can be heteronuclear. An example of that is, we'd say, water would be the most common. You have two hydrogen and one of oxygen, and they're chemically bonded. Okay, so now that is that is that. Now, the one thing about it, where do I differ? You know, in my channel, I tend to always be a little bit out from the common perception. And when the electrons go around, when they go around each other, they spin round. They spin round, and they would spin out of control, so that you couldn't have any universe or any atom or any element, because the weak, strong nuclear and magnetic forces are so powerful that they would be unstable if you didn't have control. And it's the same if you went to a city and there were no speed limits and drivers had an unbelievable wish to drive extremely fast. You'd have utter mayhem. You put a speed limit up to restrict the speed and you try and enforce it, and as a result you get the flow of traffic, because the cars could be made bigger and bigger, and the lorries, so they could go 200 miles an hour in a city, which would be a disaster. Same with the atom, there has to be a limit. And the limit is imposed by SOL, the speed of light. It's not that light can only travel at that speed, but light is the only phenomenon that can travel unrestricted. If you let it go in a vacuum, it'll go at as fast as it can go. And if there was no limit, then it would go so fast that it couldn't work. But where I differ is that this speed of light is within the atom itself. It's the speed of light limit that keeps the electron, the proton, and the nucleus going round each other in an orbital, which is limited, which can only go at a certain speed. It's not only in the light that's emitted from the atom through electromagnetic radiation, it's the spinning of the components of the atom, the particles themselves. It's their spinning. So the electron here is limited by the speed of light, the same as the light emitted from the disruption of the atom is limited also. Everything is limited. And that is part of Albert Einstein and other scientists which went at the time of him. That is their great discovery. There's a limit on the speed you can go in the universe, and radio waves are electromagnetic radiation and are very close in character to the speed of light. And so radio signals coming from very distant places take a long time to get to Earth. That is the reality, and all speeds are the same. So my claim, my scientific claim to fame is that the speed of light, now this is not really denied by scientists, it's not that there's a conflict, it's just a different way of putting it. This speed of light limit goes right into the center of the atom. There are massive forces in an atom. An atom contains unbelievable amount of energy, all locked up with these forces. They have to have a shape. The shape is a spinning orbital, similar to the solar system. In many ways, a bit like the solar system. Only that you would have the sun and a sister planet, a binary planet, two planets together, and then you'd have the sun and a binary star. The sun is a star. You'd have maybe two proton, neutron, two stars, maybe a big one and a slightly smaller one, and that does exist, and yet if the planets going around it, that would be the electrons. So it's the same idea that nature selects, the orbital. In the case of the solar system, the thing that keeps the parts inside it is gravity, which is not fully understood. I will not go into it here, but they're held together by those four forces which are driving the particles round like that, and they're at the same time the speed of light is just stopping them at the very speed that would be destructive. So the speed of light keeps them at that speed, and therefore the atom is stable, and therefore we can have our universe the way it is. There are some great mysteries attached to this. I'll deal with them in another time. But what you need to look for, if you see science for children, it will be an extension of this. If you don't see children in the caption, in the heading, and all of the description of the video, then it's something else. This is all suitable for children, and all that, and it's very, very, very interesting, and it is strangely true. when they try to see an atom, sometimes they appear sort of grey, sometimes they appear sort of light green. They never appear as red. They seem to be a greeny colour. Now, having seen them is very difficult, and sometimes there can be little lines dividing them. Now, when you have, we'll say something that I'm very familiar with, an element of iron, they're held together by these forces, and when you heat them up with a blow lamp, you get to a point where they melt like a blacksmith's forge, and a blacksmith heats it up till he gets it almost hot. But what he does is he stops short of that and he shapes the iron. But if you continue to heat it, it will turn into a full liquid. They will sort of half stick together. They'll half sort of stick together, but you can pull it apart with anything. But if you let it cool, they form an unbelievable strong bond. And what's happening there is that the particles inside in the atom are going around so fast that they lose a lot of their ability to attract. They're flying around at an inertial speed, they expand a bit, the forces that are holding them together weaken with the high heat, and they eventually just run and flow. And if you heat them enough, they'll evaporate, and the steam or the vapor or the gas that comes out of them will just simply float away in space. Okay, so that's the first lesson of my scientific talk for children. I hope you enjoyed that. Give it a thumbs up or a thumbs down. The atom is the smallest part of one of the 95 elements which you can have without having a catastrophe of a nuclear explosion or whatever. And everywhere around you, that's what you are seeing. They're shaped into certain ways. Our world is the way we see it, but in actual fact, we are also made up of atoms. And when I look at something here, or look at the camera, or look over there, or look out the window, this is all, there's atoms everywhere. And my eyes are using atoms. And the electron in my brain are causing signals to transmit the image I see from the reflection of the sunlight and the lamplight, to image it into something of a shape that I can see. That's unbelievable stuff. Unbelievable. Hope you enjoyed that. Right, we leave it at that and see how that goes. Is there any, as they say, is there any interest or any call on science? And if there is, I'll continue. If there's not, I'll not push something that people don't want to see. Bye, folks, and please give me a thumbs up or thumbs down or criticize as you wish. Bye.